So now we have seen how to compute correlation. So let's go ahead with model building. So we are going to be looking into two algorithms. One is linear regression and other is the random forest regression. And for each of these algorithms, we are going to use two sets of data. Now the first data is obtained by removing any missing value. So any row with any number of missing value gets omitted. So even if it's a single row with one missing value, the entire row gets omitted. Now the other data is where I impute the missing value. So I'm not going to let go of the missing cells. I'm going to come up with some algorithm that's going to help me impute the missing value. So these are the two sets of data, and for each of these set we are going to use a linear regression model and a random forest model. So let's start with the first data, which is by omitting missing rows, right. So the command that you are going to use to drop any data with a missing value is drop NA. I am setting the axis as equal to 0 because I want to drop any row that contains any number of missing value, be it 1 or be it all cells missing, right. And once the command is executed, so the remaining data gets saved on to cars_omit. We started with 42,772 records, and after removing all rows which were missing, it came down to 32,884, and that's roughly about 10,000 records that's been removed. So once it's omitted, cars_omit, and you can see that around 10,000 records have been removed. So we have columns that are categorical in nature, for instance vehicle type or gearbox or model. Now the values under these columns are strings in nature, and none of the machine learning algorithms under scikit-learn accept columns which are strings by nature. So I am going to dummy encode these categorical columns, and I am going to generate newer columns out of it. For instance, let us say if your fuel type is diesel, petrol, and you have CNG and LPG, you have 4 categories here, then I am going to generate 4 minus 1, which is 3 more columns out of this. One column will have fuel type underscore diesel, the other column will be fuel type underscore petrol, and similarly you have columns generated on it. Now the value under each of these columns will be 0 or 1. Now 0 if it is not present and 1 if the value is present. For instance, let us take the column fuel type. Now this column has several values. Let us say you have a column called fuel type underscore diesel, and if diesel is present under this, then that column will be, then that cell will be marked as 1, otherwise it will be marked as 0. So ideally we are trying to encode all of these categories as zeros or ones alone, and we are going to get rid of the strings. So in order for us to do that, I am going to use the get dummies function from the pandas library, and I am going to drop the first category. So if I run it, you will see there are 301 columns in total. So we started with 10 and then we have 301 more, and the reason is because you have several categories under each column, and especially variables like brand and model have several categories under them, and hence you are getting more number of columns. So before we proceed, let us just begin by importing some of the necessary libraries that we might need. Now I am importing the train test split from scikit-learn.model_selection. Now because we are going to go about building a model, we will need a train set on which we are going to build a model, and we also need a test set of data on which we are going to test it. So given this data cars_omit, I am going to reserve a certain part of it for training and building my model, and I am going to reserve the remaining part to test my model on. And for that you need the train_test_split function, and I need the linear regression function from sklearn.linear_model, and like how the name suggests, this is for building a linear regression model. And similarly for a random forest model, I want the random forest regressor, and this is a part of sklearn.ensemble package. And apart from these two, there are a few heuristics that I am going to calculate, and one of it is mean squared error, and that is a part of the sklearn.metrics package. So I am going to import these 4 libraries or packages before I proceed. So let us begin by separating the input features and the output features. Now my input features I am going to call them as x1, and my output feature, which is price, I am going to call it as y1. So from cars.omit, I am going to drop only price and I am dropping column. So, I am just mentioning it as columns and I am just saying in place equal to false. I do not want the changes to be reflected under cars underscore omit, right. So, let us just drop only price. So, basically x1 has everything apart from price. So, cars underscore omit had 301 columns and one column alone we have removed, which is price, and hence you have 300 columns under x1. Contrary to that, we want y1 to contain only one column, which is price. So, I am just saving cars underscore omit and within square indices I am just giving price, which makes it y as only column and you have the same number of observations for price. Now, this is, so x1 is a collection of all input features and y1 is my output feature, which is price. Now, I am just going to plot the variable price. Now, before I plot it, I am just converting it to a data frame which says before and after. So, y1 and then I have transformed y1 as a log, as a natural logarithm. So, let me just run this command. So, basically you will have two columns under prices, one is before, the other is after. Before is what you have as y1 and after is after taking a natural logarithm. Now, the reason we are doing it will be clear when I plot the histogram, which is below. Let me just drag the screen to show you the difference between plotting histogram with y and plotting histogram with logarithmic of y. So, here you can see there is a nice bell shaped curve the moment you plot the x axis as natural logarithm of y, whereas on my left I have just done a histogram on just the price, whereas on the right I have a logarithm of price. Now, here you can see that the shape, the right hand side is more bell shaped or normal compared to the left is more skewed, and this itself tells you that we should consider going further with a natural log on the prices and not just with price. So, we are not going to regress price with the input features, rather we are going to regress the log of price with input features, and this log is the natural log. So, let us now transform the price as a logarithmic value. So, I do np.log of y1. So, my entire y1 is now transformed, right. This is because the range of price is very huge. Because you want to avoid it, you are taking a log. Now, I am splitting my data into test and train. I am just dragging the output window to the right just to show you the entire command. So, the train underscore test underscore split is the function which we have already imported. The input to it is the input set of features, the output set of features, which is x1 and y1 respectively. Now, the test side I am giving it as 0.3, and which means 70% of the data will go to the train set and the remaining 30% will be retained as the test set. And I am setting a random state of equal to 3. So, now random state is a predefined algorithm. It is called pseudo random number generator. You can give any value to this parameter and I am giving a value of 3. So, every time you run the same algorithm, the same set of records will go to train and test. So, the output I am saving it as x train, x test, y train and y test. So, the x's represent the input set of features and the y's represent the output feature, which is price. So, let me just run this command, and once I run the command I am just printing the shape of each of these. So, my x train is 23,018 and again have 300 columns. My y train is 23,018 again. Similarly, my x test is 9,866 and I again have 300 columns, and my y test is 9,866. So, this is the shape of the data. If you do 23,818 divided by 32,884, that is roughly about 70%, right. Similarly, if you do 9,866 divided by 32,884, that is roughly about 30%, right. You can infer the test train split ratio from here itself based on the number of observations. So, before we move further, we want to build a baseline model for this data. And in the baseline model, the predicted value is basically replaced with the mean value of the test data, and this is to actually set a benchmark for us and to compare our models that we are going to build in future. So, for this data we are going to build a regression and a random forest model, and in order to compare the metrics from that model, we also need a base value or a base metric, and the base metric that we are going to use is the RMSE value for the base model. So, the base model is where you replace the predicted value as the mean from the test value, and that I am saving it as base underscore pred, right, and that comes out to be around 8.25, and I am going to, so this is only one value and I want it repeated to 9866 values, which is the length of y test. So, I am just replicating this value over 9866 records. Now, I want to find the RMSE value. Now, RMSE is root mean squared error, and it is a, like the name suggests, it is the square root of the mean squared error. So, it computes a difference between the test value and the predicted value, squares them and divides them by the number of sample. Now, that is mean squared error. The moment you take a root of that value, you get the RMSE value, which is the root mean squared error. So, you already have a function called mean underscore squared underscore error, which we have imported earlier. Now, the input to it is the test data, right, the y underscore test, and the base predictions, right. So, these are the two values that I am going to give, and once I compute it, I am just going to print it. So, the base RMSE turns out to be 1.13 roughly. So, this is our benchmark for comparison. Any other models that you are going to build in future should give you an RMSE that is less than this. So, that is the objective for us. So, now let us start with linear regression for this data. Now, I am going to call this the omitted data because I have removed all missing values from here. So, the function that you are going to invoke first is called the linear regression function. I am setting the intercept as true because I want an intercept for this, and I am saving it on to an object called LGR. Once you do that, you need to fit the model on the train x and train y, train x being the input features, train y being the output features for the train set of data. And I am storing the model as model underscore linear underscore 1, linear is represented by lin, and once I do that, I want to predict my model on the test set of input features. So, my test set of input features are the x underscore test, and I am going to use the dot predict function, and I am saving my predictions onto cars underscore predictions underscore linear 1, linear again is represented by lin 1. So, here you can see you have 9866 predictions, right. Now, these are my predictions. Now, I am again going to compute my mean squared error. Now, instead of giving a base predicted value, I am going to pass on the actually predicted values here, and again the other parameter that I am passing is the test set of features that I have from my test set. Now, again I need a RMSE value, so I am just computing the RMSE by taking a square root of this, and if you print it, you will see that my RMSE for this model, which is a linear regression model, is 0.54. So, we started at a value of 1.12 with the base RMSE, and we came down to about 0.54, that is roughly about a 50% drop, right, there is a 50% change from this value. So, we have come down a long way from where we have started. So, we are at 0.54. Now, let us see if we can compute the R squared value. So, the R squared value tells you, so how good is your model able to explain the variability in the y. Now, let us do this for test and train. Now, I am going to call the function dot score from the model underscore lin 1, and the input to it is x test and y test, and similarly if you want to R squared value for your train, you just give the train input. Now, I am just calculating the value of for test and for train, and let us just print it out. So, if you print out both these values side by side, for the test set my R square is 0.766, and for my train set the R square is 0.780, cutting quite close, but the train seems to be definitely better, and the test is not far behind, it is about 0.766. So, that is a close cut. So, this tells you that the model is good. As much as the variability that the model was able to capture in the train data it's able to capture the same amount of variability, if not more, on the test data itself, on the test data as well. Now, let us just do a quick regression diagnostics. Now, I am going to calculate something called residuals here. Now, the residual is nothing but the difference between your test data and your prediction. Now, the residual is nothing but the difference between your predicted value and your actual value. Now, your actual value is under y underscore test and your predicted value is under cars underscore predictions underscore linear 1. Now, once you do this, you can plot. Once you do this, I am going to generate a residual plot using a simple scatter plot, where my x is the predicted or the fitted value, that is cars underscore predictions underscore linear 1, and my y is nothing but the residuals. So, let us just quickly do a regression diagnostic. I am going to use the residual plot analysis. Now, I am going to generate a separate set of numbers or values, that is called residuals 1. Now, it is the difference between the y test and the cars underscore prediction underscore linear 1. Now, basically residuals are nothing but the difference of your actual value or the observed value and the predicted value. So, that is called residuals. And what I am going to do is I am going to generate a simple scatter plot, where my x axis is basically the fitted or the predicted values and my y axis contains the residual values. So, let us just do a quick scatter plot here. So, I am going to drag the output window a little to show you how does the plot look. This is good because you want the residuals to be close to 0. Since residuals are more of errors, you want the errors to be less, and that tells you that your predicted and your actual values are very closer. And this can also be seen from the describe function. So, if you do a residuals 1.describe, this gives you the summary of the data, and you can see that the mean of the data is around 0.003, that is very less, it is almost 0, right. And this itself is a good indicator that your predicted and your actual values are very closer now, and this is the conclusion that you can actually draw from your residual analysis. So, I have just shown you for one linear regression model, and you can just do it with the others as well. So, let us move ahead with random forest model. Now, a random forest model has several inputs, and we have already imported the function called random forest regressor. So, I have a couple of parameters here as input arguments. Let us just quickly go over what these mean. So, in my help toolbox, I have typed scikit-learn.ensemble.randomforestregressor, and it gives you a quick description of what does the function do. But if you come down, it also tells you what are the input parameters and what do they mean. Also mentioned under the parameters are also the default values. So, let us begin with the first parameter, which is n underscore estimators. Now, because this is a random forest tree, you can have several trees, and that is what n estimators does. It basically tells you the number of trees in your forest. The next is maximum depth, which is the depth of each tree, how deep do you want each tree to go, and that is given by maximum depth. The minimum underscore samples underscore split is the minimum number of samples that is required for a node to split. So, let us say if you have only 2 observations in a node and you do not want that node to split any further, right, because it might not make any sense. So, in that case, if you want to impose such conditions, you can do it here. The next is minimum underscore samples underscore leaf, and it is the minimum number of samples which is required to be at a leaf node. And the next input is maximum features, which is basically the number of features the algorithm wants to consider to build the model or to build the tree, right. Now, there are different options for this. If you give auto, then it automatically chooses, otherwise you can give square root, which is basically the square root of the number of features. So, each tree is built on different features. So, there are other parameters as well which you can explore, one by one, and these are the main parameters that you usually start with. Again, random state is equal to 1 because I have just chosen one random state, so that every time I run the model I get the same output. So, now let us just load the function. Now, RF is the model. Now, I do rf.fit to fit the train data. Now, this will take some time. Now, the model was built using the train set of input and output features. Now, I am going to predict this model on the test set. Now, if you see under cars underscore predictions underscore RF1, you again have 9866 predictions. Okay. Now, we are again going to compute the mean square error for this, and the RMSE turned out to be 0.44 roughly. Now, this itself is a good indicator that your random forest is performing better than your linear regression model, because the RMSE has come down further. Computed the R squared value here. So, let us just print out the R squared value. So, I have the R squared value here now. Now, the R squared value for the test is 0.85 and the R squared value for the train on the train is 0.92. So, definitely random forest is working a lot better compared to the linear regression model, at least for this omitted data. So, now let us go ahead and impute the missing cells in our data, and let us now build the same linear and regression. Now, let us build this linear regression model and random forest model on the data where these missing values have been imputed. So, I am using the same cars data that we earlier started with. I am using a dot apply function, and within the apply function I am declaring a lambda function. Now, the lambda function will fill the missing values with median if the data type of the column is float, otherwise it will fill the missing cell with the most frequent category. Now, the second condition will be applicable wherever your column type is object, and the first condition will be applicable wherever your column type is float. Either ways both cells will be imputed. Now, if you impute and then you can check the number of null values under each, you will see that none of the columns have missing values. So, in our data we had missing values only for the categorical columns, and in that sense all these categorical columns are imputed with the most frequently occurring category. Now, let us convert the categorical columns into dummy variables. So, I am going to use the same get dummies function. So, if you look at cars underscore imputed, you again have 10 columns, and when you do a dummy variable encoding, you get 304 columns. So, these are the number of columns that have been converted to dummy variables. So, let us again repeat the same drill where I separate the input features and the output set of features. Now, I am again plotting y2 what you get and np.log of y2, and if you plot a histogram you can again see that value for price is normally distributed, and this is the same as before. So, all our predictions are going to be for a log transformed value of price. So, I am going ahead and I am transforming it to a natural logarithm, and then I am going to split the data into test and train again, and I am using the same split ratio which is 0.3, and if you print the shape you can see 70% of it has gone to train and remaining 30% have gone to test, and here are the individual split up of the test set and the train set for the input and output features. So, let us again start by building a baseline model. Now, here I am going to use the y underscore test 1. I am going to find the base RMSE for this. This is the same function as before, and just that by instead of having y underscore test, I am doing y underscore test 1. So, that is the only change that is here, and in this case we have a RMSE value of 1.18. So, again let us go ahead with linear regression. I am going to repeat with the same set of steps. I am building a model, I am fitting the model with the train data, and then I am predicting the test data. So, this is the RMSE value. So, I am going to use the same function again, and if you print the RMSE you can see it is 0.648. Now, after imputing you can see that the RMSE value for the linear regression model has gone up, right. It was earlier at around 0.56 for the same data but without cells which were missing. So, the error has gone slightly up. Now, let us go ahead with random forest model for the same data. I am again building a model with all parameters. I have kept the parameters value the same as before, just to standardize both the methods, and I am again fitting the model on the train and predicting on the test. Again this will take some time to run. So, the model has run and it has predicted it on the test set. So, let us just compute the RMSE again, and the RMSE that you get in this case is 0.494. That is a lot less compared to what the linear regression model gave with the imputed data. So, again let us compute the R squared value for this, and R squared value for the random forest regression model after imputing turns out to be 0.83 for the test set, and on the train set it is about 0.9. Now, that is a very good R squared value compared to the linear regression model that we had got earlier, and similarly even if you look at the RMSE value, we had got about 0.49, and that is a good value compared to the linear regression model on this imputed data. So, let us just print all of these and condense it together. So, basically I am just printing these values so that we can infer the message. So, what I am printing here is basically a condensed form of whatever we have computed till now. I have taken two sets, one is a set of metrics for the omitted data and the other set of metrics for the imputed data. Now, for the omitted data you can see that the R squared value for train from the linear regression is 0.78, again on test it is 0.76. So, it is more or less close, and similarly for random forest the R squared on train is 0.92 and the R squared value on test is 0.85. Now, if you look at the base RMSE value, it is 1.12, and for this data for linear regression the RMSE value turns out to be 0.54 and the RMSE value from random forest turns out to be 0.44, and these are also the heuristics that we have computed earlier. So, this tells you that definitely on at least the omitted data, the random forest is definitely performing a lot better compared to the linear regression model. Now, moving further to the imputed set of data, if you look at the R squared value from the linear regression on train it is 0.70 and it is more or less the same even on the test, and if you look at the R squared value from random forest on the train it is 0.9 and on the test it is at 0.826. So, that is again a good value and it is a lot better compared to your linear regression model, and the base RMSE for this data is at 1.18 and the RMSE value from the linear regression that you have got is 0.64, but however, if you look at the RMSE from the random forest it is at 0.49. So, definitely for the imputed data there is a huge remarkable change in the RMSE value between your linear regression and random forest model. So, your random forest model is definitely a lot better than your linear regression model, and this is very important because it is okay if the models are performing good for data where missing values are omitted, because in that case you have a clean data, you are very full. But more often than not, problem comes only when you start imputing cells, because you are not sure about with which value you are supposed to impute and how the results are going to turn out, right. So, at least in this case the imputation looks like the imputation has not gone really wrong, and random forest definitely is a lot better than linear regression, and this is also very important to impute values, because you do not want to let go of information and you do not want to let go of the number of records that you have. In the earlier case where we did omit, we lost about 10,000 records, we had around 33,000 odd records, but after imputing you can see that random forest is definitely able to capture the variations much better than linear regression. So, it is necessary that you do not let go of information that you already have, but at the same time there is a trade off between how much you can retain and how much you can leave. So, thank you.